Your behavior in fire. My name is Tony Takahashi from West Reserve University, USA. So the first speaker is from please introduce your self and then presentation title.
Alright, thank you very much for coming to my presentation. And before I start my presentation, I would like to introduce myself. My name is Mohamad Ramadhan, and currently I'm a PhD student in the University of Queensland. And today I would like to present my paper with the title of the experimental study on the flammability and burning behavior of live and dead eucalyptus salicta foliage. And this paper is also written with my UT colleagues, which are Sergio, Geronimo, Andres, and also Juan Hidalgo. And we are from the Fire Safety Engineering Research Group, School of Civil Engineering, the University of Queensland. Starting from the very broad question, why wildfire nowadays are getting more severe? Is it only because of the climate condition, or it is also because of the change of the fire management or the fire risk assessment? To answer this question is a long way to go, but now we have to focus on what is actually wildland fire. To understand about wildland fires, we need to understand more about the vegetation field, also the fire behavior, which defines how the fire could behave in the environmental condition, also the fuel flammability, which defines the capability of the fuel to ignite and sustain the fire, and also the current tools to quantify the fire danger. Australia has a really high diversity of vegetation. There are forest fuels, grassland fuels, and also shrubland fuels, with approximately 70% of Australia's land were covered by grassland fuels. But in here, we'll only focus on the forest field by using the eucalyptus trees, because more than 80% of Australian forests were dominated by eucalyptus trees. Those vegetation species could contribute to different wildland fire behavior. In wildland fire behavior, there are surface fire, which usually consumes the litter, grassland fuels, and also understory species. And it is usually spreading in the horizontal orientation. And the second one is the crown fire that could happen when the heat from the surface fire is enough to preheat and combust the fuel above that. Also, when the crown fires is happen, usually it is followed by the active spreading of fire from one tree to the other tree canopies. The most interesting part in here is there is one part of vegetation that could contribute to all the fire behavior, which is the foliage. Why? Because the foliage exists in each strata of the wetland fuels, such as in the ground or surface, in the understory shrubs, and also in the tree canopies. Also, wetland fires are generally spread faster through the foliage compared to the other vegetation parts, such as trunk, bark, and etc. Also, the foliage or leaves has a really high surface area to volume ratio, which makes that the foliage is extremely sensitive to the environmental changes. And until now, a lot of fire risk model use the foliage to assess the wildland fire behavior. However, this wildland fire behavior is very depending on the flammability of the wildland fires. In the fundamental of fire science, we divided the flammability into two parameters. The first one, the ignition parameters, which defines the ignitability of the fuel, and the second one is the flame spread parameters. But in here, we just only focus on how the fuel could at least sustain the fire. The flammability parameter could also be used to assess the wildland fire danger. Previous work by Lutfi et al. Has defined the wildland fire danger using two different dangers. The first one is the ignition danger, and the second one is the propagation danger. And in here, it is interesting that the fuel moisture content is one of the factors that could influence to both of the danger, which are ignition and also propagation. But until now, there is still lack of study on what is actually the difference between the dead or live leaf. And until now, a lot of fire risk model still assuming is only using the dead leaf to estimate the total wildland fire behavior. And also, there are a lot of assumptions that the live leaf is only wet or moist dead leaves. So that we need to answer that what is actually happened between the dead and live leaf. And that is why the objective of this paper is to study the difference in the behavior between the dead and live leaves under fire conditions. And to achieve that objective, we are doing the experimental approach using some apparatus. The first one is the environmental chamber. So that we can get the variation of the moisture content for the leaves. And also we are using the moisture balance or moisture analyzer to measure the moisture content of the sample right before the test. And for this first step, we are doing the characterization test using the simultaneous thermal analyzer to perform the thermographimetric analysis. And in the thermographimetric analysis, at first we dried and powdered the sample, the leaf sample first, so we can make sure that we have the homogenized sample. And we set the instrument to be performed at a heating rate of 20 degrees Celsius per minute, from 20 to 900 degrees Celsius. So it is covering all of the decomposition process of the leaf. And we are using two different gas carriers, which are nitrogen and also air environment, so we can get the differences between in the different environment. And for the flammability test, we are using the mass loss calorimeter to measure some flammability parameters, and also to perform the measurement of the mass loss of the sample. And in here we are using the standard sample holder with the size of 10 times 10 times 5 cubic centimeters, with the various radiant heat flux from 25, 35, and 50 kilo per meter square. And for the sample that we use we are using the Eucalyptus saligna trees because this is one of the most common species in Australia. And there are two leaf conditions. The first one is the live leaves, which is collected directly from the trees. And visually, we can see that the live leaf is still green in color. And in the structure, the live leaf has bound water, which is the water inside the cell that cannot be extracted easily. And also, live leaves has some free water. And the second one is the dead leaf, which is collected from the fuel dealer in the ground. In visual, the dead leaf is already brownish in color, which means it is already decomposed and decayed naturally. Different with the live leaves, the dead leaves only has free water, which is the water content that can extract it easily. Before we do the flammability test, we are conditioning the sample first. There are three conditioning processes. The first one is the fresh sample, which means the sample is directly tested right after the collection process. And the second one is the oven dried sample, which is the sample is dried first using the oven dryer, so we can get the really dry samples. And the last one is the sample that is conditioned using the environmental chamber, so we can get the wide range of moisture content from each sample. So from that, we get the moisture content for the live leaves from 4 to 120% of moisture content in dry leaves. And also for the dead leaves, we get the range from 3 to 14% of moisture content. And to minimize the variation of the result that is influenced by the fuel load or fuel structure, we fix the dry bulk density for each test, so we can make sure that the condition of the fuel bed is the same. So here's this characterization result for the thermographimetric analysis. In here, for the first one, we analyzed using the nitrogen gas carrier. And as the lignocellulosic material, there are 4 processes that happen in the Eucalyptus saligna leaf, which could be represented by the derivative thermographimetric curve. The first one is the moisture release, which usually happens in here in the first peak, and usually happens in between 80 to 100 degrees Celsius. And the second one is the decomposition of the hemicellulose, which could be represented by the first shoulder here, and usually happen between 200 and 300 degrees Celsius. And the third process is the decomposition of the cellulose, which happened in the first peak in here, and usually happen between 350 to 400 degrees Celsius. And the last process is the decomposition of the lignin, which could be represented by the last figure here. If we compare the differences between the dead leaf and the live leaf, we can say that it is similar. We cannot conclude anything from here because in the characterization test it's pretty similar, even though the deadlift has a little bit higher rate for the decomposition of lignin. And next, we are comparing for in the air condition, which is there is one more step, which is the oxidation of the cellulose and also lignin. But again, we get the similar result between the deadlift and also live lift, even though the deadlift has a slight higher rate for the decomposition of lignin, also oxidation for the cellulose and lignin. But still, it doesn't mean that much. And now we are moving on to the result, the influence of the moisture content of live and deadlift. The first flammability parameters that we measure in here is the ignition, which is representing the ignitability of the fuel itself. And here we are measuring the ignition delay time with the variation of the moisture content. And we get the similar result with the previous research, that the increase of the moisture content will delay the ignition time. And from this result, we can get the linear correlation between moisture content and also ignition delay time. And we can use that equation to assess the flammability of the materials of the sample. With the higher slope means less flammable. So if we compare the deadlift with the live lift, of course, the deadlift has higher flammability compared to the live lift. Of course, because of the different moisture content. But is it possible to use the correlation that we get from the deadlift to estimate the behavior of the ignitability of the live lift? From this, we get 3 different regression model, linear regression model with different heat flux. And in here, we are trying to use the equation that we get from the live lift correlation to estimate the deadlift ignitability. Also, we are using the equation that we get from the deadlift to estimate the ignitability of the live lift. And here is the result. So for this one, it is written live lift, which means the observed ignition delay time of the live lift using the experimental measurement compared with the estimated ignition time of the live lift using the equation that we get from the deadlift. Okay? In here, we get the results that the estimated value are overestimating the observed one. While in the deadlift, which means the observed ignition delay time of the deadlift using the experimental approach, compared with the estimated ignition delay time of the deadlift using the equation of the live lift. Actually, the results are pretty agreeable, but still, most of the estimated value are underestimate the observed one. So that from here, we can know that it is not reliable to only use one condition of the leaf to assess the total wetland fire behavior. Also, the moisture content will also have an effect to the burning rate, which is represented by the peak mass loss rate in here, or we can say the peak energy released by the combustion. Again, we get the similar correlation, which is linear, with the increase of the moisture content would decrease the peak mass loss rate. And if and that could be happened because the moisture content in the solid phase would behave as the heat sink because of its specific heat will absorb the energy that could be used for the combustion. So that the energy that the energy will be absorbed by water itself and make the burning rate is decreased. And if we compare the deadlifts with the live lift, we only can compare in the relatively low moisture content, which is in here in below 12% of the moisture content. And from that we can see that even though it is the same, it is almost the same for the moisture content, is 12. The value of peak mass loss rate or peak burning rate of the deadlift are still higher compared to the live lift. This could be explained by the different structure inside of the lift. Because in the life leaf, there is still a bone cell or structure cell that when the heat is coming, it is the heat will decompose the structure cell first, and then the moisture will be released and also applied as the heat sink again. And now we are moving on to the results by comparison of the flammability parameters between the live and dead leaves. The first one, we are measuring the threshold measurement of the mass loss rate. Again, in here, it is the oven dry condition, which means the moisture content should be the same between dead and live leaf. But we get different results from here. It is perfectly like what I explained before. And if you are seeing this for the fresh condition, which is the moisture content of the dead and live leaf is different, yeah, they will get the different result because of the moisture content will behave as the heat sink that is absorbed the energy that could be used for the combustion process. But what is actually the role of moisture content? A lot of previous research assuming that the moisture content would be totally released right before the ignition. But in fact, the combustion still could be happen or occur before all of the moisture is released. And also, it is not only the evaporation process that is happening. The pyrolysis process also occur and release the volatile matter. So in here, we are comparing the mass loss during the pre-ignition process, also the mass loss during the flaming combustion, and also the mass loss during the smoldering combustion. Now we're moving on to during the pre-ignition process. In the relatively low heat flux, as we can see that the mass consumed during the pre-ignition are higher compared to the higher heat flux. Why? This could be explained by two possible reasons. The first one is when the relatively low heat flux is applied, the fuel bed will behave as the thermally thin material, so that there is no thermal gradient inside of the fuel bed, and that we can assume that all of the moisture content will be released before the ignition. Or the second reason is the evaporation process will be occurred at the same time with the pyrolysis process, with the same heat, with the same rate, so that when the volatile is released and creates the flammable mixture, the moisture content will dilute the flammable mixture and delay the ignition time. Right. And in the higher heat flux, it is different phenomena. In the higher heat flux, there is the fuel bed will behave as the thermally thick material, which means there will be thermal gradient inside of the fuel bed. So as long as the top layer of the fuel bed is ready to be ignited, the combustion will be occurred. That is why the mass loss during the pre-ignition process of the higher heat flux are lower compared to the lower heat flux. And then during the flaming combustion, the dead leaves consume more mass compared to the live leaves. Because the water inside of the live leaf will behave as the heat sink that is absorbing the energy to be used for the combustion. And for the smoldering combustion, it is only consuming the remaining char from the flaming combustion, and it is also very depending on the energy left after the flaming combustion is extinguished. And here is also for the mass loss for the oven dried sample, which means the moisture content for both leaf sample should be the same. But again, we get different mass loss during the pre-ignition, while the moisture content is the same. Why? McAllister has analyzed that the live leaf has more mineral content. In here, she analyzed that live leaf has more carbohydrate and also fiber, which makes the mass loss during pre-ignition of the live leaves are higher compared to dead leaves. While we got the results for the mass loss during flaming and also during the smoldering are quite similar with the previous result. And here is the comparison of the flammability parameters we are doing the statistical analysis to compare some flammability parameters here, such as time to ignition, time to reach peak burning rate, time to flame out, peak mass loss rate, and also residual mass fraction between the life and death leaves. And as you can see in here, that in the relatively low heat flux, in the 25 kilowatt per meter square, a lot of variables that is insignificant. So we can say the materials are quite similar or the same. Yes, because the material will behave better thermally, so the moisture content inside of the leaf itself should be released totally. And when we are applying the higher heat flux, there are more significant result or difference. That could be explained by this conclusion, that the moisture content and the leaf condition have a direct influence to the flammability and fire behavior. Also, the moisture content will behave as the heat sink by its specific heat, by absorbing the energy that could be used for the combustion. And the last one is the moisture content will also delay the mixing process of the flammable mixture in the reaction zone. And from that, we get one big conclusion, that we need to justify the treat of the live and dead leaves correctly, and not to assume that the live leaves are the dead leaves with the higher moisture content. And that is all for me, and thank you very much.
Lutfi Chatterjee from Global. So at the end, nice talk. At the end, you had that last set of plots where you showing the mass loss rates. Can you just go over? So I just you gave a very nice explanation that Sarah McAllister rates were. Yeah, but what is the reason that for the dead leaves, this normalized mass loss, which I don't understand the normalized part yet, but decreases with increasing heat flux? See this red, the red.
Okay.
Yeah. What is the explanation for that?
Yeah. Actually, for this, I don't really have a clear explanation because we didn't do until the mineral analysis, something like McAllister did. And also we couldn't explain from the moisture content analysis, because actually the moisture content is already the same for the open dead sample. So yeah, actually I still don't have any clear explanation for this, but when I read the McAllister works, that she has only showed that with the live leaves has the higher mineral contents compared to the dead leaves. So if for the live leaves, so the plus is increasing. So in the relatively higher heat flux, which is the higher heating rate for the pre-ignition process, there are more minerals that could be released right before the ignition compared to the dead leaves.
Next
That's
question.
good.
Do you have a question? Yes.
Yeah, I'm thinking about a question about the comparison of the results of the TGA and also the later physical analysis. The TGA analysis results showed us that the dead material and the live material, they have essentially the same chemical species. You can see that the TGA and also the mass loss rate, they have almost the same results. But the later analysis shows that the ignition time and other parameters, they have very significant differences. So can you have a comment about the physical essence about the difference of the two kinds of samples for the flammability? What's the real physical significance of physical essence about that?
I don't know, because actually maybe for the thermographic analysis, we conditioned the sample first, so it's dried and powdered. So it's almost the same visually between the live leaves and the dead leaves. It's dried and also it is powdered. While in the flammability test, we are using the raw of the leaf, so we didn't condition it much. We only conditioned the moisture content. So probably the difference between the thermographic analysis result compared to the flammability test one, it is because of the structure cell of the sample itself is already different. And also in the thermographic analysis, we are only using 10 milligrams of the sample, which means probably this small gap in here would be more meaningful in the larger scale of the experiment.
Okay, one more question. Yep.
So your sample, you put the leaves together in a sample holder.
Yep.
Do you think that varies how the leaf actually burns? Because leaf burns in a single sheet with black
Yeah.
surrounding it.
Yep.
So now you have a sheet over top of a sheet. So your conclusion might be unique towards that situation.
Sorry?
So your experiment finding might be unique towards how you made up the sample.
Yep. That's why in here, yeah, actually, we can say that the type of the field bed of this type of the test is the porous medium. So it's different. It would be different behavior with individual leaves compared with the porous medium. So yeah, in here we are a bit different. Yeah.
Okay, thank you.